Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everybody. It is my great pleasure to welcome Joachim Anden here from the École Polytechnique in Paris. We sort of got lucky. He was in town visiting some folks at UW and had some free time. We were able to snatch him and come and give us a talk on his very interesting work on scattering transform, which is sort of having lots of interesting applications in audio and image processing. And without further ado, I'll let him take away. And we should also say congratulations. I believe he has defended his thesis recently, and in 2 days we'll start a postdoc at Princeton. So he only has 2 more days of his freedom left before between jobs.
Thank you. Yes, so my name's Joachim. I met some of you already, and I'm going to talk about some of the work that I've been doing together with Stefan, my advisor, during my PhD thesis these last few years. And so my thesis has been mainly concerned with classification of audio signals. And one of the problems in classification is we want to model our different classes of signals very well in order to be able to identify in what class to put an unknown signal. The problem is we have a lot of different types of variability in audio signals that's not necessarily very important. We can have shifting in time, we can have stretching in time, we can have transposition in frequency and so on. That's not necessarily that important, but nonetheless takes up a lot of training data if we want to construct a good model of it. So for example, we have these 3 sounds, which are the same word pronounced differently. And as you can hear, ask, ask, ask. It's pretty obvious that they're the same word, but we see on the spectrogram that we have very different properties in terms of pitch, duration, and position relative to the center. And so we have all this data. We want to be able to model it well. We want to be able to model all this variability well, but it's not very useful for determining the class of the signal. And so this is one of the problems. And what's usually done to solve this is, instead of trying to model the waveforms directly, we have an intermediate representation that reduces the variability of the data in order to allow us to construct models without having as much training data. And so we don't want to reduce too much information because we want to be able to keep what's important for classification. But this is not necessarily very obvious. We don't necessarily know what type of information is going to be important for the classification task. So what we're going to do is we're going to take a very conservative approach, and we're going to say we know what we don't need in our representation. We know what's not going to be useful for the classification task. And this is going to be transformations of the signal that don't affect its class. And we want these transformations not to affect our representations either. And so this can be time shifting, this can be frequency transposition, and so on. But on the other hand, we want to keep as much discriminability as possible. So just a quick overview of my talk. I'm first going to talk about time shift invariance and how it applies to audio representations, specifically the scattering transform. And then look at how the scattering transform is able to capture certain discriminative properties of audio signals. After that, we're going to look at transposition invariance, how we can extend this representation to get something that is invariant to shifts in pitch, which gives us another type of scattering transform. And then finally apply these to 2 different audio classification problems. And so the way we formalize this mathematically is we just take our signal, we shift it in time by a constant, and that's our time shifting. And what we say is that a problem is invariant to time shifting if a given signal is still in the same class after we shift it in time. And then we require a representation also to be invariant. But we also have a more general class of transformations of the signal, which are time warpings. And so this corresponds to taking a signal and then deforming it slightly in each position. So it doesn't have to be a constant deformation, which would correspond to a translation, but it can vary with position. And this means that it also includes dilations. You have locally a time warping like this is going to be a deformation. And the larger the deformation, generally the more different the sound will be. It will induce changes in pitch, changes in duration. And so what we want to say is we don't want to be invariant to time warpings. Instead, we want to be stable in the sense that small time warpings, which have little effect on how we perceive the sound, little effect on its class, we want that to have a little effect on the representation. But for larger time warpings, where the sound is going to sound very different, we want the representation to change a lot. So we have what's called a Lipschitz continuity condition, or a stability condition to time warping, that we're also going to require. This is in fact a much stronger condition. We have lots of representations that will satisfy time shift invariance, but not necessarily time warping invariance. An example of this is the spectrogram, which is commonly used, but not often for classification directly. And the reason for this is, while it is time shift invariance, in the sense that if we do a small time shift with respect to the window size, we don't have stability to time warping. Specifically, if we take a pure dilation where we have a linear time warping, we see that for a sample signal like this, where we have a harmonic stack, in the low frequencies, we overlap significantly in the original signal and in the warped signal, but in the higher frequencies, we're not going to have the same thing because the shift is going to be proportional to the center frequency. A solution to this is to average the spectrogram in frequency, which gives us the Mel-frequency spectrogram. And the important thing is, when we average it, we want it to be constant Q at high frequencies, because this constant Q filter bank is going to ensure that we compensate for the increased movement in the high frequency components. And the result is then, after averaging, we have something that overlaps just as much in the high frequencies as in the low frequencies. And we can see that for this example, the difference between the Mel-frequency spectrograms is going to be on the order of epsilon. And what's interesting is that this representation has been motivated mainly from psychoacoustic and biological directions, by saying that this is something that we see generally in the cochlea. But it turns out that there's also a mathematical justification in terms of time warping stability why we want to have this type of averaging. And so, as a summary, whenever we have a signal and we want to create a representation of it, if we use a spectrogram, we're going to have problems. We're going to have invariance to time shifting, but we're going to have instability to time warping. But a constant Q average will stabilize this problem. And so, in order to look at this a little deeper, the problem with the Mel-frequency spectrogram is that it's not very useful to characterize larger scale structures by itself. And to see why this is, we're going to slightly reformulate the definition. The way we calculate a Mel-frequency spectrogram is we take a spectrogram and we average it in frequency, like we saw just before. Another way to get something that's very similar, it's not exactly the same, but contains a similar type of information, is to take these filters that we use to average and instead convolve the original signal with them, which gives us this time frequency representation that is very high frequency, that is very high resolution in high frequency, and much more regular in low frequency. And then we average this in time to get a regular time frequency grid, like in the case of the Mel-frequency spectrogram. There is a way to show this mathematically, that we have equivalence between the averaged filter response amplitude and the Mel-frequency spectrogram, but I'm not going to go into that right now. And a way to view this is to say that we have a wavelet transform. Now, a wavelet transform is sometimes thought of as this sort of dyadic decomposition where you have one octave that's taken up by the wavelet coefficients, and then you decompose and take the low-pass filter, and then take the high-pass octave of that, and so on. But there's actually a lot more flexibility that we can put into it. For example, we can have much more narrow response in frequency, which gives us this constant Q wavelet filter bank. And so it's going to be constant Q in the high frequencies and linear in the low frequencies, but it turns out this is not necessarily that big of a problem. And we're still going to call them wavelets, even though they're not exactly wavelets. But they have a lot of the nice properties that we need from them. And what's also interesting is this is going to give us basically a Mel-frequency scale as well, just by having this type of constant Q filter bank. So using this, we can define a wavelet transform, which is a low-pass filter, which captures the low frequencies that's not in the bandpass filters, together with the bandpass filters then. And if we make sure that we cover the whole frequency axis, we get an invertible transform. And so we can now say that the Mel-frequency spectrogram can be thought of as a time-averaged wavelet coefficient amplitude. Now, if we look at the wavelet decomposition, the modulus of these, we see that when we average them in time, we lose a lot of information in terms of temporal structure. And this is one of the reasons that Mel-frequency spectrograms are not very good if we want to characterize completely a large-scale structure. Because if we increase the averaging scale, we're going to get something that's more invariant, but we're not going to get something that that captures the temporal dynamics of the signal. And so we have a loss of temporal structure. We need to capture this fine structure, and the question is how. One approach that's been used is modulation spectrograms, but the problem is if we take a modulation spectrogram, which is going to consist of taking a spectrogram of each of these separate channels, we're going to run into problems again because we're going to have the instability to time warping. And so we need to look at a different method for capturing this high frequency information. Yeah.
So just so I'm clear, seeing these two pictures, on the right is the sort of normal Mel frequency filter with the time averaging triangles. And on the left is a series of sort of actual bandpass filters.
Yeah, exactly.
And then you're taking the modulus of the energy in those.
Exactly. And then they're averaged to get a Mel-frequency spectrogram. It's not technically the same. And so, just to digress a little bit, the information is contained, if we reduce the window size, we do retain more information in the Mel-frequency spectrogram in the sense that we do have the sequence of vectors. But the problem is we're then going to need a classifier, a model on the back end to learn which specific sequences correspond to a certain class and so on, and this is what the HMM does. And what we want is we want to relieve the model of the responsibility of learning the temporal dynamics. And so we want a representation that covers a large duration of time, but that captures as much information as possible. And we see that if we try to do that with the Mel-frequency spectrogram, we're going to run into trouble because we're just going to lose more and more information.
So here when you cross off the modulation spectrogram,
Yes.
to indicate that that kind of transformation is going to destroy the information?
It's not going to destroy the information, but it's going to capture more information that we would like. It's going to capture a lot of details that's not necessarily important. And this is kind of the idea of stability to time warping. Because if we're unstable with respect to time warping, that means that we sense changes in the signal that's not necessarily that important, that corresponds to these high frequencies that can move very quickly, even though there's not a big change going on. And so the modulation spectrogram, because it takes a spectrogram of these signals, and the spectrogram has this instability property, means that we're going to run into problems. Now, what you can do is you can take the modulation spectrogram, you can average it along modulation frequency using a constant Q filter bank. And then you get, some people have been doing this, so it's like a constant Q modulation spectrogram. And then you do have a stable representation. And that's going to be similar to what we're going to end up doing, actually. Yeah.
So the kind of things that less group is doing.
Yeah, I mean, he's done both, I think. I think he calls it modulation scale when he does the constant Q averaging.
And that's okay in terms of
Yeah, that's better. Yeah, that's much better. Because then you lose the sensitivity that you don't really want. And so that's similar to what we're going to end up doing. And so the issue is that when we take this wavelet modulus and we average it, we lose information. So we're going to see how we can recover that information. And so just as a small sidebar, these filters that we're considering, they're analytic filters. So they have no negative frequencies. And this means that when we take the modulus, we're actually going to get a nice, or somewhat nice, envelope estimation of the signal, because it's going to correspond to taking a real wavelet coefficient and then computing a Hilbert transform of it. So when we take the modulus, we're going to get the Hilbert envelope of each subband. And then what we do to get what's equivalent to... Sorry, do you have a question? No. Right. What we do to get our Mel-frequency spectrogram is we average this in time. And so we basically just recover the low frequencies of this envelope. Now, the rest of the information is then going to be contained in the high frequencies. And we see that since the wavelet transform is invertible, we can think of this low-pass part as just the low-pass part of a wavelet transform. And so we know that the rest of the information is contained in the high frequency coefficients of a second wavelet transform then, that we apply to the envelope. The problem is that these coefficients don't have the invariance and stability conditions that we want. And so we take the modulus again and we average. And so we get this, these are called then second order scattering coefficients. These we call first order scattering coefficients and second order scattering coefficients. And so we have as many first order coefficients as we have first order frequencies. And these correspond then to acoustic frequencies, corresponds to a certain subband that we're looking at. And then we have this second decomposition, which is then corresponds to more something like modulation frequency. We look at each subband and we decompose it and we look at the different types of oscillations present in there. Another way to formulate this is to look at a very similar transform, which is a nonlinear transform, which is the wavelet modulus transform. We take the wavelet transform, we apply the modulus to the wavelet coefficients, and this gives us a basic building block for constructing these types of coefficients. And we essentially get a cascade that we apply to our original signal x, and out of that we get an average, which is just the average of the signal, which in audio we're not going to care about. Most of the time it's going to be 0. And then we get these first order wavelet modulus coefficients is what we call these. Then we reapply the operator to these coefficients, and we get what's called the first order scattering coefficients, and then second order wavelet modulus coefficients. Then we reapply, get second order scattering coefficients, and so on. So technically this can go on to infinity, but we're going to see that that's not going to be necessary, thankfully. And so the structure of this is basically a convolutional network. We have convolutions followed by nonlinearities followed by convolutions. One of the differences is that here we capture information at each layer as opposed to just at the end. And also the filters aren't learned. Instead, they're fixed to be wavelets. And this is not to replace any sort of deep neural network methodology. Rather, it's a complementary approach. The reason that we don't learn here is because we know that we need the invariance condition, we need the stability condition, and then once we have a representation that satisfies this, the idea is that we can then plug it into a deep neural network that will then have less problems learning these invariance and stability properties because we've already encoded them in the representation.
The nonlinearity you talk about here takes what kind of form?
It's the modulus. It's a simple modulus. So that's all it does.
So only
but it's necessary.
That nonlinearity condition, do you get invariance?
If we remove the modulus, our invariants are going to be all 0, because we're going to have all sorts of linear operators, and the only linear invariant you can get from a signal is its average, and so we will get 0. So the nonlinearity allows us to create more and more invariants from our signal.
Type of nonlinearity is desirable. Can you imagine some other kind of nonlinearity?
Yeah, I mean, you could. We haven't done experiments in audio. We have done a little bit of experiments in audio, and it turns out that the choice of nonlinearity is not all that important. Like you could replace it with like a local max, or they've been doing other stuff in images, and it turns out that it's not that important, the difference. The modulus is nice from a mathematical perspective because it turns out that if you want the stability condition and if you want your transform to be contractive, it turns out that you're restricted to have a pointwise unitary operator, and so it's going to be the modulus maybe multiplied by some complex numbers. So there's ways of showing that, but experimentally, it doesn't seem to matter all that much.
So this only guarantees invariance how can you make sure you still conserve information for discrimination?
Yeah, I'm going to get to that because it's not entirely obvious that you're discriminative from this. And so the idea is that whenever we lose information from averaging, we recover some of it with the high frequencies of the wavelet decomposition. But then we lose information again, and so we recover it again. So the idea is that whenever we lose information, we recover some of the lost information, and so that's how we remain discriminative. But it's...
So probably I don't understand what is the meaning of that last convol with phi?
Here, yeah. So that's an averaging in time.
It's just averaging over time?
Yeah. All of these convolutions are in time. So here we capture just the average of the signal. Here we take the signal, we take a certain bandpass filter, we take the modulus, we compute the envelope, and then we average it in time to get something that's invariant and stable. And then since we've lost information here in the average, we recover it in the high frequencies here in the second wavelet decomposition, take the modulus, and average once again. And so it's to get these invariants that we need to average, because otherwise we're very sensitive to shifting and warping.
And that Wavelet transformation includes the filter bank, Mel scale filter bank.
Yeah, these are both. The first one is a Mel scale filter bank, sort of. It has about 8 wavelets per octave. It turns out that we don't need to use the same wavelets in the second decomposition as the first decomposition. So here, it's more like a traditional wavelet filter bank. You have 1 wavelet per octave, or 2 is what we found works best. But these are the basic parameters of the representation: how many wavelets per octave, and how large you want to make the averaging. Yeah.
Are you going to cover? I think it was the Lipschitz, the dilation, how that comes into play in terms.
Yeah,
of...
a little bit. Yeah. I think it's the next slide. Maybe. Yeah. Hold on. Yes.
Just one question.
Yeah.
So, with the exception of the modulus, this looks like a dyadic filter bank.
It's not completely dyadic because we have. Well, it depends on what you mean.
Well, I mean, if you were to choose a wavelet such that under dyadic scaling, the scaling function is orthogonal to the previous scaling.
Yeah.
You no longer have that orthogonality. Does that matter in this case?
I'm not quite sure I understand what you mean.
Perhaps you could talk about this offline afterwards.
Yeah, no, I mean, it's... these wavelets are not necessarily the same wavelets that you would have in like an orthogonal wavelet decomposition. In fact, these wavelets are very redundant, and we would like them to be. If we had wavelets that were orthogonal, we would run into problems, it turns out. And so these are actually very redundant wavelets. They overlap significantly in frequency, and they have a non-zero scalar product. And so it's not necessarily the same framework that you would have in a dyadic orthogonal wavelet decomposition. So it's
try to minimize the amount of overhead, amount of redundancy. And here you're trying to
exactly
more.
Yeah, you want to be more redundant, because if you're more redundant, you're more flexible to these types of changes. Like a time warping won't suddenly shift one coefficient into another bin and then you're completely lost. And so you want to have a certain type of redundancy. And it also makes sure that when you take the modulus, you don't lose quite as much information. So it has all sorts of nice properties, the fact that we are redundant. So these are wavelets, but they're wavelets in the very sort of general sense. They're wavelets in the sense that they're dilations of a mother wavelet, period. And barely even that in this case. And so the important thing is that they're constant Q. That's what we care about. So it's less related to like orthogonal decompositions and so on. So we can continue this cascade and then get for a given m, we get an mth order scattering coefficient. We can put all these together into one big vector, and we get what's called a scattering transform or scattering representation. We define a norm on that, and with this norm, we get this theorem which proves the Lipschitz stability condition that we were talking about earlier. And the reason that this holds true is basically if you have a wavelet and you apply it to a deformed signal, you can do a change of variables so that it's equivalent to the original signal on a deformed wavelet. And this is not going to be drastically different from the original signal because a deformed wavelet and the original wavelet are going to be relatively close in terms of Euclidean norm. This will not be true in a Fourier decomposition, for example. A sinusoid and a deformed sinusoid are going to diverge significantly at a certain point. And so that's kind of the heart of the argument, but it's like a proof that runs for 10 pages, so don't ask me to go into detail. But that's the basis of why it works. So we have this nice stability condition for this representation. We also have lots of other nice properties like conservation of energy. If we have a wavelet transform that conserves energy, we also have, as a consequence of this, that the amount of energy in each order decays. And so it turns out for most applications, we can just look at first and second order coefficients. We also have that when we demodulate, we get something that's essentially low frequency. And so we don't need to keep the same sampling as we had in the original signal. So we get like this graph I was showing you earlier. And the high frequencies were very irregular and the low frequencies were very regular. So it lets us save in computation and space. It also means that once we decompose this using the second order wavelet decomposition, we don't need to take, here we need to take a lot of high frequencies, but here we can get away with just looking at the low frequencies. And we see this, for example, looking at the second order decomposition here, where we plotted the first order frequency, the acoustic frequency, and then the second order frequency, the modulation frequency. We see that a lot of this is going to be zero, and so we could neglect to compute them. And the result is we get an algorithm that runs in about n log n to calculate these coefficients. Now, the question is, what sort of information do we have in the scattering transform? We've seen that we are discriminative in the sense that we capture a lot of the high frequencies, a lot of the temporal structure that we've lost, but what exactly does this constitute? And so we're going to look in the case of audio of a simple model which consists of an excitation filtered by an impulse response and then modulated in time by an amplitude A. And the question then becomes, what sort of information can we see is recovered by the first and second order coefficients in this type of model, which is a relatively constrained model, but it still allows us to look at some simple phenomena. So for example, here we have three sounds with the same excitation, harmonic excitation, with different amplitude envelopes. First is a smooth envelope, then we have a sharp envelope with a sharp attack, and then we have a sinusoidal amplitude modulation, a tremolo. We can listen to them. I think, yeah. And so we hear they sound quite different, and we see here in the scalegram in the wavelet modulus decomposition that they look quite different. But when we calculate the scattering coefficients, what we're going to do is for each of these channels, we're going to isolate them and we're going to average them in time. And so we're going to lose the distinct characteristics of each of these envelopes, and they're going to turn out to look more or less the same if the window size is large enough. If we need a certain amount of invariance, we're not going to be able to capture this information directly. And this is essentially what we would see in the Mel-frequency spectrogram with this window size. However, if we capture then the second order coefficients, which is going to be this signal, but decomposed using a second wavelet decomposition, then the modulus, and then averaged in time, we do capture the differences in the envelope in the sense that here we have mainly low frequencies, and that's represented here in the display, in the second order coefficients. Here we have transients, so we have high frequencies, and here we have a sinusoidal modulation, and so that's represented as a maximum around that frequency. So we see that we capture these different properties of the envelope in the second order coefficients. Whereas the first order will mainly give us information about the type of excitation and the filter, the spectral envelope, the filter H. And we can replace this by a stochastic excitation, a white noise excitation for E, and we're going to end up with similar results. And we can hear that these are also relatively different sounding signals. But yet the first order does not necessarily see any difference between these three signals, whereas in the second order we're able to differentiate between the three. The difference between this and the harmonic case is that here we do have a low-level noise floor that's due to the stochastic excitation that also is seen in the second order. So we do have a bit of a bleed over there. But we do capture the information on the envelope as well.
So typically you only use 2 orders?
Yeah, for right now we've only looked at 2 orders, and it's in classification results it's usually enough to get good results. But I'm going to get to that in a little bit.
When you showed the so you, on the bottom figure in the previous slide,
Yeah.
what kind of value was it evaluated for lambda 1?
It was hold on, I'll go back. Yeah, so that's important. So these are, I fixed 1 lambda 1 for this particular display, and so it's at this frequency at 2,400 hertz. But in reality, you have a whole sequence of these displays. But you would need some sort of 3D representation that it's a bit difficult to do. But yeah, so this is for 1 fixed frequency channel that I've showed this for. But you're going to see something similar in all of them, because the envelope is the same at all frequencies in this model. So you're going to see that.
So how many dimensions do we have for the lambda 1?
It depends. I mean, in the test that we've looked at, it could be around 40, 50, up to 70. And in the second order, it could be in the 100, 200s, yeah. I've calculated this for a very dense sampling, so this is not representative.
When you see 100 to 200, you mean for each values in the first order you have 100? Or the third order?
No. I mean, for each time frame, for each point in time, I have about 50 first order coefficients and 200 second order coefficients. Just about. It depends on the parameters. But on that order, yeah. So we can also look at frequency modulation, as you heard just now. We have sinusoidally modulated pitch and a constant pitch and an amplitude, sinusoidal amplitude modulation. And what we have is, this is also represented in the second order in terms of this harmonic structure here, which is different from the amplitude modulation when we just have a sinusoid. The problem is we can also create an amplitude modulation here, which sounds different from the frequency modulation, but gives us very similar second order coefficients. And so this shows us that there is a certain drawback to this type of scattering representation, in that it doesn't really show the difference between AM and FM. But it will detect the presence of either one.
And those would be the same at every lambda 1?
No, they would not, exactly. So this is for this fixed one, it would be the same, but it's not possible to make them exactly the same for most of them. But they're difficult enough to tell apart that I think it will cause a problem in modeling them. You don't have a very clear distinction between the two. But yeah, this is just for a fixed lambda 1. Finally, the final example we're going to look at is looking at frequency components interfering. So if we have 2 notes that are played together, as opposed to played separately, in the first case they will interfere, and you'll have a beating phenomenon in the envelope that's going to give us a maximum in the second order coefficients. So we can listen to them. And so in a sense, the dissonance that you hear between the 2 notes is captured here in the second order coefficients, a certain type of roughness. And another way to think about this is to say that since we have a certain bandwidth of the first order frequency filter bank, we lose information about absolute position, but the second order is going to give us relative position information about different frequency components in each frequency band. So to summarize, in terms of this model, what we can see is that first order coefficients tend to capture very short time structure, like looking at excitation, looking at the filter, which is going to be, in these cases, around up to 10 milliseconds of duration. Whereas the second order coefficients is going to characterize larger scale structures like amplitude modulation, frequency modulation, and interference. So we have this kind of separation of scales between the first and the second order coefficients in what they characterize. Another way to understand what type of information is captured in this representation is to look at reconstruction from scattering coefficients. And what we have is we have a result that says that for certain wavelets, we can, in fact, invert the wavelet modulus operator. And since the scattering transform is a cascade of this operator, we can cascade this to get an inverse of the scattering transform. The problem is, to calculate this inverse is a non-convex optimization problem. It can be relaxed somewhat, but it's still intractable for the types of audio signals that we're looking at. So what we're doing is actually we're using an approximative heuristic approach to recover this, which is a basic alternating projection algorithm, like a Griffin and Lim sort of approach. And so to get the original signal, we can cascade this inverse wavelet modulus operator. The problem being at the end, we won't have the necessary wavelet modulus coefficients, and so we have to use a deconvolution to get our first order estimate. So there's errors involved in this process, obviously, and since this is approximative, we get errors, and so this is not a perfect reconstruction. I would not recommend using this in some sort of fancy audio codec or anything, but what's nice is it gives us an idea of what type of information is captured in the first as opposed to the second order. And so we can see this for a speech signal where we have the original signal.
Vital questions would be quickly answered.
We have the reconstruction from just the first order,
Vital questions would be quickly answered.
where you see that certain parts have been smoothed out. You lose a lot of transients that we have here, for example. But if we add the second order coefficients to the first order coefficients and reconstruct from that,
Vital questions would be quickly answered.
we do have a large amount of artifacts, but we hear that the attacks and the transients have been restored to a certain extent in the reconstruction from the second order. So this kind of confirms what we saw with the models in that we do capture that type of temporal dynamics in the second order.
So when you say invertible, do you mean if you have m equal to infinity, then you can recover the original signal, or is that what you
Yes, if you had a good... Yes, yes,
Only
the answer is
while
yes.
m equals to infinity, basically.
Yeah,
Okay.
but in reality, no, because what happens is each time you take the modulus, you're pushing your energy, you're pushing your information to the low frequencies. And so at some point, most of your information will be captured by the low-pass filter. And so you won't have to continue to decompose anymore. So at that point, your deconvolution is going to be trivial. You're going to be able to recover your wavelet modulus coefficients fine, because your averaging won't have done anything. And so then you can theoretically recover. The problem is we're using not a very good algorithm here, and so once we cascade it far enough, we're going to have all sorts of errors that will accumulate. And so actually adding the third order to this is not going to improve. But if we had a good algorithm to invert, then yes, it should, yes.
So in theory, do you have any proof that as the term gets higher and higher, the errors gradually getting smaller, aside from this algorithm part?
In theory, yes. I don't. It should be true, yes. But I don't think we've proved or looked into the details of it. But intuitively, it should, yes. But yeah. So we don't only have we have lots of types of variabilities in audio signals. We're only going to touch upon a few of them here. And so, except for time shift invariance, we also might want to have frequency transposition invariance. And so here, for example, we have one word pronounced by two different speakers, and we have a difference in pitch, but also different in format frequencies. And so we can listen to them.
Encyclopedias.
And so we hear that they're the same word, but we don't have the same pitch information. And we see here in the formants, we don't have the same format information. And what's especially interesting is we don't have a pure scaling of the frequencies. We don't have a shift in pitch or a shift in formants that's constant over the whole spectrum. Instead, we have a different shift at different parts of it. And so the distances between the formant peaks is going to vary. And so this corresponds more to a frequency warping than a pure frequency transposition. And so this tells us that we might not just want to be invariant to frequency transposition, but also stable to frequency warping in the same way that we saw with translations in time.
That's a very dangerous one. Because if you warp that a little bit different, you might change from one sound to another sound. So how do you build that kind of discrimination back to over here so that
well, the idea is that
they don't confuse?
Sorry. The idea is that we're not completely invariant to these types of frequency warpings. We're stable to them, which means that a small frequency warping is not going to change your representation very much. So a small change in the formant frequencies is not going to change it very much. A large change is going to change it more. So your representation will be able to hopefully separate between the important changes in formant frequencies and the less important ones. But if you guys probably know this better than I do, but if you have a formant frequency that shifts slightly, if that's going to change the idea of your vowel, then you're going to run into trouble with this type of thing. Yeah.
So are you able to constrain your warping in such a way that these special cases when confusion will occur, it's not a effect?
The answer is not explicitly, but it turns. What's nice with this continuity condition is it tells us that we have a continuity with respect to these time warpings. And what that means is that a warping is going to be realized locally as a linear transformation in the representation space. And so what's nice then is if we have a linear discriminative classifier at the back end, it's going to be able to project against certain directions and in that way create a real invariance to certain time warpings while maybe increasing sensitivity to other time warpings. So since we linearize time warpings or frequency warpings in this case, this classifier should be able to decide which ones is important, given enough training data, of course. But so that's kind of a nice property that comes out of it. But since we don't have, if we had pure invariance, then yeah, that would become a problem because then you might run into these types of issues.
I have a remote question, all the way from California. So I didn't tell you, half our team is actually in the Bay Area. So Malcolm Slaney, who you may know, is asking the question, and I quote, "I believe the Hilbert transform only makes sense as an envelope follower if there is only a single component in the subband, signal frequency component. So does the theory still make sense when the Hilbert, I guess the question is, does the theory still make sense when the Hilbert transform doesn't actually give you the true envelope?"
I mean, because the idea here is that it's nice to be able to formalize it as looking at the envelope of a specific frequency component, but it's not necessarily crucial to have it be specifically an envelope. And we saw, for example, in the case where we do have two frequency components in the same filter bank, in the same filter response, what we do see is we don't get the envelopes of each one separately. Instead, we get the beating phenomenon between them, which in our case is nice because it gives us information about the internal frequency structure in the filter bank, which we wouldn't necessarily have if we just looked at the individual envelopes present in there. So it's not necessarily dependent on having an exact estimate of the envelope in this case. What's important is having a nonlinearity that brings us to the low frequencies. It just happens that in some cases we can interpret it as an envelope when we just have one frequency component. So I hope that answers your question. Great. Okay. So there are some approaches that have been done to get this type of transposition invariance. One first perspective is to say that transposition frequency, which is a scaling of frequency, is going to be a translation in log frequency. And so log frequency and Mel-frequency, in high frequencies, Mel-frequency corresponds to log frequency. And so at these frequencies, we can simply average the Mel-frequency spectrum, and we get something that has this transposition invariance. And this is basically what the Mel-frequency cepstral does in taking the low Q-frequency coefficients in the DCT, which amounts to an averaging along the Mel-frequency scale. The problem is, once we start averaging along frequency, we lose information. And so we can gain some invariance by doing this, but if we try to gain more and more invariance to capture larger and larger scales, we're going to lose more and more information, and so we're kind of limited in that sense. Another approach is, you guys are probably familiar with, is vocal tract length normalization, where you try to realign the spectrum of at a given point with that of a reference speaker using a sort of scaling coefficient. An advantage of this is that we don't lose information because we're just simply rescaling the whole spectrum, but it's sometimes problematic to estimate the scaling coefficient, and if we don't estimate it exactly, we don't have the desired invariance property. Another problem is that we don't have the stability to frequency warping unless we start considering nonlinear warpings of the spectrum. But then you run into problems of you have a large search space and so on. And so these approaches have their advantages, but in this case we lose information, and in this case we have a certain instability. So the approach we're going to take is that instead of averaging along log frequency, we're going to take the scattering transform along the log frequency scale. We fix a time point t, and we go along log frequency, and we compute another scattering transform, and so on. And this gives us the separable time and frequency scattering transform, or just a separable scattering transform. And it's nice in the fact that it has the invariance that we want to time shifting and frequency transposition. And that, of course, depends on the scale that we consider here with the scattering transform. We could decide to have a small scale or a large scale, but it captures more information than if we just done a simple averaging. And in experiments, we usually can restrict ourselves to the first order coefficients. It's usually enough at the scales that we consider. The problem is that this approach, and actually the approach of the original scattering transform, loses a lot of important information because we decompose each frequency band separately, and we average each frequency band separately. And so, for example, these two signals, if we look at the regular scattering transform with the window size that covers the whole signal, it's going to think that they're going to give the same exact representation because we have this same frequency band here as here, but shifted in time. And so since we don't capture any information on the correlation between frequency bands, it's not going to be able to tell the difference. So we lose this joint time-frequency structure. And so a way to solve this is, instead of decomposing each frequency band separately, we would like to do as in Shiab Shamma's cortical representations, where we decompose this time-frequency scaleogram in 2 dimensions, in time and frequency simultaneously, instead of doing as in the separable case, where we decompose just once along the temporal domain, and then once and then average, and then once along the frequency domain. And so here we get then a 2-dimensional wavelet that we use to decompose the scaleogram. And we can then form, like we did before, a wavelet modulus transform and cascade this onto the scaleogram, and this gives us what's called the joint time-frequency scattering transform, or the joint scattering transform. And so this has the advantage of having the same invariance and stability as the separable scattering transform, but it captures more information in that it's able to distinguish between these cases where we've shifted individual frequency components. And so it captures correlations between frequency bands. And we can also create a representation that is sensitive to frequency transposition by omitting the averaging along frequency and just averaging along time. And this gives us something that has the same invariance properties as the regular temporal scattering transform, but that captures more information. So finally, we're going to look at some classification results to try to validate some of these claims. And the first is to look, yeah.
Sorry, if you go back here. So what's the net difference between sort of what this time frequency scattering transform and using like a Gabor bank of kind of Gabor filter banks?
It is. We're using Gabor filters. Yes, it's a Gabor filter bank. Yeah. I mean, this has been done, I think, by.
What's the second? Is it the second order then applied again?
So here, the first order is going to be x. Here is the. I had it in the previous slide. X is the the scalegram, the wavelet modulus coefficients, the amplitudes of the wavelet coefficients from the first order. So the first order wavelet decomposition stays the same. And then on that, the second order decomposition, which includes this low-pass filter and then this wavelet decomposition with the modulus and another low-pass filter, forms the second order decomposition. And so, but it's going to affect the first order as well. But the decomposition is regular wavelet transform, then two-dimensional wavelet transform, and then you reapply the two-dimensional one, and so on to get the higher order. But we're just going to concern ourselves with the second order for now. So does that answer your question? Or? All right. We can come back to it. Yeah. So to try this out, we look at the TIMIT task of phone segment classification. And excuse me. What we do is we try to classify a segment where we're given the beginning and the end, so it's technically cheating, but it makes for an easy problem to code and to test, so that's what we did. But it does give us interesting results on the different types of representations. And so what we do is we take the scattering transform over about 160 milliseconds and we compute it using 32 millisecond frames. And we put this all into one big vector that we then put into an SVM, and we train a classifier with that. And then the goal is then to try to classify the phone that's in the center of this segment. And the results that we have first is that we see that we perform similarly to the delta MFCCs with the first order coefficients. And so here L equals 1 means that we have first order, L equals 2 means we have first and second order, and then first, second, and third order then for L equals 3. And so the first order coefficients perform similarly to the MFCCs, which is what we expect since they carry similar type of information. In the second order, we do see a certain improvement of almost 2% absolute, which shows us that the temporal dynamics that we capture within each of these frames is actually useful for this type of classification. The third order, we actually do worse. And the reason for this is that when we look at small time scales, as I said earlier, when we apply the modulus, we're going to force energy towards the lower frequencies. And that means that once we get to the third order, we're already very regular, we're already very low frequency. And so it's not going to be very important to capture the high frequencies in the wavelets. And so in the third order, we're going to have a lot of noise. We're not going to have very much information. And so it's not going to help us classify in this case.
MFCC does mean that you feed that into SVM.
Yeah, in the same way as, so we take delta MFCCs over 32 milliseconds, and then we concatenate them over this whole big segment, and then we feed them exactly as in the scattering case to make it comparable.
I thought the error, doing such a way just that won't be so low. So
we also include the log duration of the segment.
Oh,
That makes about 2% absolute difference. So that might be why. Yeah.
What's the state of the art?
The state of the art is, I think, Jim Glass. So it's like a committee-based classifier with different segment lengths and stuff, and so they get 16.7%.
Features are there in total in each of the cases?
Delta MFCCs in first order, it's around 50, I think. Second order is, like I said, around 200. Third order, I think it's like maybe 500. But I'm not sure about the third order. I know it's about 200 for the second order.
It's a lot of features.
What?
It's a lot of features.
Yeah. But I mean, we're using an SVM, so it's not necessarily the end of the world to have. If we were using GMMs, when we started this, I was using GMMs because I figured that's what everybody does, and then I found out the results were not very good. But yeah, so you're going to have trouble if you try to choose some sort of generative model like that. But the SVM does handle it pretty nicely.
And the DNNs we use now take about 1,000 features.
Yeah, I mean, I did some experiments where I did like huge vectors of 10,000, it was able to do it. Yeah, so this is what I was talking about. So if we want transposition invariance, what we can do, which is quite nice, is we can skip the frequency averaging. And since we're using an SVM, the SVM is going to optimize a locally linear discriminative plane at each point. And so if we have enough data, it should be able to learn how much it wants to average for each class pair. And so that makes it so that we don't have to decide how much transposition invariance to enforce on our representation, but instead we can depend on the SVM to learn it if we have enough data. And so we tried fixing the averaging scale and then not averaging in time, not averaging in frequency, and letting the SVM try to learn it, and it turned out that that was much better. So that's what these results show. And so to compare for the second order scattering coefficients, we have 17%. If we add scattering transform on top of that along frequency, we get 16.5%. So almost a 1% absolute improvement. And then for the joint case, where we then capture more time frequency structure instead of just temporal structure, we do improve somewhat again over the separable case. So we also looked at musical genre classification, because that's something that everybody does, so it's nice to be able to compare. And so this basically consists of having 30 seconds of music, trying to classify it into 1 of 10 genres. And then what we do is we do for each 700 milliseconds, we classify that, and then we vote over the whole track to try to get a result. And so again, we get results similar for the first order and the delta MFCCs. Once we add the second order, we get a big improvement of about 40% relative. And the difference between this and the previous cases, here we're looking at much larger timescales. So the difference between what the first order captures and what the second order captures is much greater. We have a lot more temporal dynamics that we need to recover in the second order. And so we do have a significant improvement here for the second order. And so the third order does a little bit better, but we're still not in the regime where we expect the third order to carry a lot of energy and a lot of information.
Yeah, so state of the art here is from George, his group, or?
State of the art, I can't remember. It's a paper from 2009 where they use modulation spectra, and then they do all sorts of like LDAs, and they sum along certain dimensions and stuff, and they get like a 9.4 error rate. I can't remember. I can send you the paper, yeah. And so this is just using an SVM, just like kind of feeding it in there. One of our colleagues who was at Princeton previously, who is now with Stefan's group, managed to get 8.8% using a sparse representation classifier on this, using the second order coefficient. So by being a little bit more clever, you can squeeze some more out of it. And for the transposition invariant case, we see that we have a certain improvement with the separable scattering transform. In the case of the joint scattering transform, we actually don't do better. We do about the same. And this can be attributed to the fact that we don't, here the issue is not necessarily that we want to be able to characterize very fine joint time frequency structure. Here the issue is that we have data points that are very, very far apart, and we want to be able to create good invariance between them. And so adding more specific information about the joint time frequency is not necessarily going to help us when what we want is more invariance, not more discriminability in this case. And yeah?
What's the type of signal there that you expect where the third order would be
well,
important?
the third order, you would expect the third order to play a larger role when you're looking at larger timescales. And so here we're looking at less than 1 second, and you can see by looking at how much energy is contained in the third order that it's not very important. Once you start looking at larger timescales than that, you expect it to do better. The reason that we didn't look at larger timescales in this case was because we didn't even if we added the third order, going beyond 700 milliseconds resulted in degraded performance. And I think that has more to do with the nature of the problem. Once we go beyond that, we start, if we have something that's about 500 milliseconds, we have a greater chance of getting a segment where we have maybe one instrument and so on. And so it's easier to characterize, as opposed to if you get a larger segment where you have to characterize mixtures of instruments and so on. And so it becomes something that's more complicated for the classifier to deal with. And so if we had a problem where we had a very large scale structure, like on the order of maybe 6 seconds, that we wanted to capture, then yeah, the third order would be expected to do better. But we haven't seen any task where it actually does a lot better yet. That's kind of the thought. But yes, so in conclusion, just looking at invariance and stability conditions for representations is a very powerful framework for trying to analyze different properties that they have with their classification performance. And the scattering transform provides such a representation that has these nice properties, and it turns out that it actually captures important audio phenomena like amplitude modulation, frequency modulation, and so on. We can extend the scattering transform to get the joint scattering transform, which captures joint time frequency structure and also gives us transposition invariance in a discriminative way. And then finally, we see that once we test this in numerical experiments, we do get state-of-the-art results in the two tasks that we looked at. And I should add that on top of this, we've also looked at classification of medical signals in terms of heart rate variability for fetuses. And we've also had some nice results in that area, but they're not in this presentation, unfortunately. So that's it. Thank you very much for listening.
Do we have examples for noisy speech or mixed speech?
No, that's kind of one of the next things to look at to see how we perform in terms of talker separation and in terms of presence of noise and so on. That's not something. I mean, TIMIT is very, very, very nice. It's very clean and there's no noise. So that's not something that we've looked at, but it's something that that would be interesting to look at in the future. But also looking at other types of distortion like clipping or masking and so on, and see how robust it is to that type of change and how we can make it more robust to that. Yeah.
Any questions? Several people have been joking this afternoon. If you did not get in there and would like to meet with them, let me know before I figure a way to make it work. All right, thanks again.
Thank you.